everyone. Thanks for coming. I hope you're not too tired. I guess it's the last presentation for the day and for the conference. And so in this presentation, I want to present some of the work I've been doing on sMATT, which is a proposal called Merkleize All The Things. And so in past presentations about this proposal, I focused more on the big theorem, on the fact that you can do very advanced stuff with this proposal. And you've seen Johan presenting progress towards implementing that with implementing the script verification, like verification of arbitrary computation in Bitcoin script. But today I want to focus more on the more simple use case of this approach. And so you've seen a lot of Merkle trees in this conference. But even if the proposal is called Merkleize All The Things, I promise there is only one slide with Merkle trees. And I think I like to start by talking about what is a smart contract and why covenants are so closely related to this idea of doing smart contracts in Bitcoin. So a smart contract is something that looks like this. Like we want to be able to lock some money inside. We want to be able to agree on some state among the parties. State means anything, any content, any variable. If you imagine a program, it could be a chess game, it could be a game of tic-tac-toe. And then you want to have some state transition rules or withdrawal rules, meaning you want to specify how the contract state can be changed by the parties in the contract. So you do some transaction, this transaction modifies the state of the contract. And so this is basically an abstract definition of what a smart contract is. And in Bitcoin, what we have is UTXOs. So UTXOs are very simple objects. You can put some conditions on how you can spend these coins. But as of today, like if you want to do smart contracts with UTXOs, we are a bit limited because you can only set some spending conditions on this UTXO. You do a transaction. So a transaction looks like a transition in a smart contract. So that's promising. But a UTXO cannot specify how the result of this transaction should be. And so if we want to do a transition with a smart contract, what we can do today is, for example, using pre-signed transactions, which you can consider as a form of off-chain covenant, if you prefer. And well, if you watched Andrew Polstra's talk yesterday, you learned how actually there is a way of using Lamport signatures to go around in a clever way on this limitation. But you can easily think that, you can easily understand that, well, if you have some covenants where allow you to program inside the UTXO how the outputs of this transaction should look like, so how the UTXOs that you produce while destroying the ones that you're spending look like, well, that looks like you're able to propagate some state from one UTXO to the other. So that looks promising in terms of doing this kind of computation and this kind of smart contracts. And the proposal that I call Merkleize All The Things is a quite minimalistic approach to Bitcoin smart contract, in the sense that the capability that you need to do this kind of contracts is quite minimal. Like many of these covenant proposals allow you to specify the outputs of the transaction. For example, CTV allows you to specify all the outputs of the transaction at once. And what we want, the core primitive that we want to achieve this capability that I call sMATT is that you want to be able to specify the program of the output. So what is the script that the output should have? So in pay to taproot, so in a taproot world, the script is basically the internal key and the tap tree, so the set of all the possible spending conditions. And we want to have some reasonable ways of controlling the amount of these outputs. And then the new thing that I want is that we want to be able to attach some small piece of data to this output. And I want also be able, if there is some data attached to the input that I'm running at this time, I want to be able to read this data somehow. And this is mostly the core primitive that we want to achieve. And the only other ingredient we need is that we need to have some opcodes that allow to do something called vector commitments. And a vector commitment means that if you have a set of elements, like what you call an array in a programming language, you want to have a simple way of compressing that into a small piece of data. And we'll see that in a moment, how we can do it. And the claim is that if we have these two ingredients, then we can do arbitrary computation inside smart contracts. And that's interesting because it means that in a certain sense, we can basically implement any possible layer 2 without needing any further changes to layer 1. And the way we do that is by using a tool called fraud proofs, which is what Johan was presenting the other day. And so what is a vector commitment? Like the simplest way of implementing a vector commitment is what we've seen a lot in this conference, which is a Merkle tree. Who is familiar with Merkle trees? Just to have an idea. Okay, most of the people. And but I'll briefly introduce how a Merkle tree is constructed. So in a Merkle tree, what you do is that you have a set of elements. In this case, there are 8 elements. And you hash each of them individually. So hashing an element gives you some form of commitment that is already very short. You can compress anything inside something which is very small. And now, if you, what you do is that you take 2 consecutive elements, you concatenate them, and then you hash the result. And now, from 8 elements, we get 4 elements. We repeat that, we get 2 elements. We repeat that, we get 1 element, and that's what we call the Merkle root. And the reason that's interesting is that now, if you want to prove that the value of a certain element is, for example, the 6th element here is x6, then the other party just needs the Merkle root, which is what we computed before as the root of the tree. And then if you look at the path from the 6th, the leaf number 6 to the root, you only need all the brothers in this path. So the node 5, the node 7, 8, and the node 1, 2, 3, 4, right? Because then, having only these nodes, which are a logarithmic number of nodes compared to the number of elements, you can verify the computation of the Merkle root and check if it matches. So this gives us a tool to compress an arbitrary large set of elements, an arbitrarily large amount of data in a single hash. And so I've been talking about sMATT as the idea, and like Johan's implementation was based on this opcode called check, contract, verify, and I like to keep them distinct because check, contract, verify is just one possible implementation of the idea. It's a very direct implementation which allows to work with this type of ideas very quickly, but it's not the only way, and I'll show some other examples of how we could get there. And so what does the opcode do? This is for more technical people who want to understand, but already you can think about the framework even if you just understood what is the idea that I presented in the previous slide, which is this one. We want to be able to control program and compute the data. And so the way check, contract, verify works is that you have this bunch of arguments. So you push some data on the stack, you push an index, you push a public key and the top 3, that's the program, and you push some flags. So those are all the arguments of this opcode. And what the opcode does is that you check that the ith input or output of the transaction, or actually the input-output, which index I of the transaction, is a pay-to-taproot script that has the given internal key, public key, and the top 3 as the program, and contains the data embedded. So what does it mean to contain the data? Well, again, that's more an implementation detail, but the way it's done in the opcode is actually that if you know how pay-to-taproot works, pay-to-taproot already commits to some data inside a public key, which is via what is called the taproot tweak. And so since we want to commit to more data inside this same public key, well, we just do the tweak twice. So the first time we tweak the internal key with the data, and the second time we tweak the internal key with the top 3. So in this way, we get a UTXO which is fully compatible with pay-to-taproot. There is no backward incompatibility in the type of scripts that we need. But yeah, it works with quite a simple. We don't require big changes to implement these kind of things. And there are some other special values that you can see below that have some special meaning, like if there are some default values, if you put -1, it usually refers to the current input, and you can use that for the index or for the internal key or for the top 3. Or if the public key is empty, as an optimization, it uses an unspendable public key, which is useful in some cases. And if you don't have any data, then it means, well, there is no embedded data, that's fine. And And what about the value of the output? We said before that we need some sensible way of also controlling the value of the output. And for many contracts, just piping the value of the input to the output that we are checking is more or less the behavior that we expect. In many cases, we have contracts that are one-on-one, so we have one UTXO that we are destroying and we are creating a new UTXO, and we just want to preserve the value. But for some contracts, for example, for vaults, it's interesting to do many to one, meaning you have many inputs that they're spending to the same output, and then you want to just sum all these amounts together. And there are some additional flags that are implemented that allow some modified behaviors. One is you can decide, okay, I want to check the program, but I don't want to check the amount. And another one that we'll see a use case later is that you can subtract the amount of this output from the input amount. What does it mean? That if you later have another call to check contra verify with a different output, then you will only check the reduced amount. So you basically pipe some of the amount to some output and then the rest to some different output, and which is niche use case perhaps, but useful for some implementations. And so I mentioned that there are multiple ways of implementing this kind of ideas. And well, the most direct way that I could come up with is with this opcode check contra verify together with opcat. I'm a weird man, so I only use opcat to concatenate things. This is not popular these days. And you can actually implement MATT with opcat alone, like Rindal was showing us the other day. And you can actually get also this kind of capabilities if you have more generic introspection on the program of the input or the output, so the SegWit program of the input and the output. Probably in that case, you would also want an opcode like optweak so that you can embed the data inside. And probably there are many other combinations that could achieve these kind of things. And after BitVM and after Andrew's talk yesterday, well, maybe it's possible today, who knows? And so in implementing these things, well, I think it's useful to just play with the tool that we have right now, that we want to discover what we can do with these things. And so my claim is that if you consider, for example, those set of opcodes that are listed there, so check contra verify, opcat, something like CTV or TXHash, and check signal stack, and tweak, plus some other opcodes, like amount introspection and big numbers arithmetic. So a soft fork with all these things is not a difficult soft fork because all those opcodes are relatively simple. And my claim is that, well, I think this can do basically anything. Like, I would be very surprised if someone can come up with an interesting smart contract for Bitcoin that cannot be implemented with this opcode. And of course, also Rusty's project of script restoration would enable MATT contracts. And so this slide is just to introduce how the framework looks like. So it's a little bit a boring technical slide just to introduce the terms. They will make more sense once we see the code. And so in this framework, what I call a contract is the blueprint of a UTXO. So it's the script and not the embedded data, but how the embedded data looks like. So, so inside the contract, you have what I call parameters, which are all the variables that are already hard-coded in the script. For example, the public keys, or if you have a time lock, it could be the time lock amount, and these kind of things. And a part of the contract is also the definition of what is the data that the contract will contain, so what the UTXO will contain. And then you have a list of clauses, which are the possible spending conditions. And because we have covenants available, clauses also specify not only who's authorized to spend the UTXO, but also what new contract and what new UTXOs are produced by the execution of this UTXO. And so instead, what I call a contract instance is something that is an actual concrete pay-to-taproot UTXO. So in this case, the data needs to be fully decided. This is a real UTXO on chain. It has an address. And so you can actually spend it if you're authorized. And so what I want to show you today is how you can go from having an idea of a smart contract that you represent as a simple finite state machine that changes from one position to another, and implement this using this concept, these ideas of smart contracts in a framework that I'll show you later. And so we already saw some presentations presenting this idea of vaults. I'll briefly introduce what is a vault again. So today, when we do a transaction, you can put arbitrary spending conditions in the UTXO, so you can make spending more complicated with multi-signature, with miniscript, with all these new tools, with Frost or whatever. But those are all measures that you take proactively, meaning before the coins are spent, you make the spending more difficult so that it becomes more secure. And the idea with vaults is that instead of doing this, we want a two-step process. We want reactive security. And so the idea is that, well, you have coins that are in a vault. We want to be able to spend it in a predetermined place. So the coins are still not out of your control. But already in this first transaction, you have to specify what is the final destination of these coins. And so they go to an intermediate state, which I'm calling here unvaulting. And then here, the happy path is that, well, you wait for maybe a day, and after the time lock expires, then the coins can finally go to the destination. And so the destination, so both of these transactions are encumbered by a covenant, because on the first transaction, you can only go from vault to unvaulting, and on the second transaction, you can only go from unvaulting to whatever is the destination. And the idea is that, well, at this point, we can add another spending condition to the unvaulting state, or perhaps even to the vault state. And this spending condition can only go to some safe place, which is some address where we secure it in a very secure way. It could be a friend who we trust. It could be a multi-signature where we have keys in deep cold storage. And it's a wallet that we don't expect to use except on emergency. So we can secure it very well because we don't use it every day. And so this is what's the idea with Vault. And so if we think about the framework we have at hand now with sMATT, we can build these state machines quite directly. We have these two contracts. So the first contract is the vault, and the second contract is what we call unvaulting. So whatever happens outside, it's outside of our smart contract at this point. And so how do the spending conditions look like? So vault has just one spending condition, which is what we described before, which is we are checking that the first output needs to be the unvaulting script, and we also want that the destination, which is passed as an argument, and so as an argument it means that it's passed via the witness. So when you spend the transaction, that's when you decide the destination. So this destination needs to be embedded as data inside the unvaulting contract. And we want to preserve the value. That's the logic that we were mentioning before. And so now how does the unvaulting contract looks like? We have these two spending paths. And so the first spending path is that, well, we want to go to the destination that we claimed before. And so we can check the time block that we can do with, depending what time block it is, with check lock time verify or check sequence verify. That's a standard time lock like we use in miniscript or on Lightning. And the other thing that we want to check is that, well, the destination needs to be exactly what was embedded in this data. And in the demo, I used that. Once we check that So first we want to check that the destination was indeed the embedded data, because as I said before, like the destination is only stored inside the input, so it's not available in script. But you can pass it via the witness, and with check contract verify, you can check the input. So you can check that indeed the destination was the data that was encoded in the script. And then the final check is that, well, you can check that the output looks like what the destination was describing. And in the demo, I did that with check template verify, which is convenient for this. You could do that with TX hash. And you could even do that just with check contract verify by checking each of the outputs you want to check directly. And, or actually, well, with check contract verify, you would only have one output instead of allowing multiple outputs. And so this is more or less what it looks like. And the final spending condition that you want is very simple. If for some reason, if someone was trying to steal our money, we don't want this transaction to happen, you have a simple script that checks that the first output exactly matches the expected recovery script. And check on try verify can do that, or CTV can do that. And again, we want to preserve the value. So this is a version of a vault. So this is inspired, of course, by the design that James O'Byrne did for Upvault. And the version in Upvault is more, has a little bit more features than what I presented in the previous slides. And it defines a sort of ideal properties that are quite compelling of what a vault should be. And the demo that I will show actually implements this version of the state machine, so it has all these features. And so what are these features that we want? Well, we want to be able to have reusable vaults, so if you receive multiple UTXOs to the same address, you should be able to use all of them. You should be able to support batching, ideally, so both you should be able to spend multiple inputs from the same vault in the same transaction, but even better if you can batch these together with other transactions, that's great because it also helps with fee management, for example. It's nice if you can allow partial unvaults, which means that in the vault transaction, you can send some money back to the vault immediately, because maybe you have a very large UTXO and you want to only send a small amount. Without this feature, your money will be locked until the time lock expires, which is could be annoying. And you want to be able to choose arbitrary unvault targets, meaning the destination should not be a set of predefined addresses. It should be any address that you decide at the time you want to start a withdrawal. And ideally should have a good fee management. And I put this slide here. This is not existing code. I started using this kind of pseudocode to document the smart contract that I implement. But the reason I wanted to present this is that you can actually think of making this a real programming language that can define fully the kind of contracts that we want to do. And I think it's interesting. It's a very succinct way of presenting these features. And this implements all the features that, even additional features that were not in the slides before. So you have these globals here are basically what I called the parameters before. So there are hard-coded variables that are hard-coded constants that are defined even before you send money to the vault. So those are the keys that you need to unvault, or the keys that you need to send to the recover, or the time block delay. And there are two contracts. This is the vault, and this is the unvaulting. And here there are two spending conditions for the vault, while in the slides I had only one, because here I have an additional spending condition that allows the partial revolt. And this is where this flag of deducting the output amount is used, and I'll show you the code, the actual code later. And so yeah, I don't have interactive demos, so you'll have to trust me if I run things on my computer. It will be the same if you run it on your computer. But yeah, there is a Docker container that has an implementation of check on try verify plus some other opcodes. And in all the demos that I'm presenting today, I'm only using check on try verify, cat, and sometimes CTV. And but yeah, there are use cases for checks from stack that are not yet implemented. And the demos are based on a framework that I've been working on that I call sMATT. In the future, I expect to work perhaps with a language like Rust, but at this time Python, I find it more convenient for prototyping things. And what sMATT allows to do is to give you a framework to semantically defines these objects, defines the contract, and also has objects that allow you, like something that I call the contract manager, that allows you to work with these contract instances to facilitate spending, deriving the addresses, and also tracking what's happening to these contracts. For example, in a multi-party contract, if someone else spends the contract, you need to be able to see the transaction on the blockchain and understand what spending conditions was used, so that you understand how the contract state changed, because you will have to react to these things. And the framework automates all these things once you define the contracts. And I have 4 demos implemented so far. So one is the vaults that is similar to Upvault. I have rock, paper, scissors, because why not? And it's very convenient academic game for playing with these things. And I have an implementation of what I call a RAM, which is just a proof of concept of using Merkle trees to work with large amounts of data inside the contract, just to store and read and write from a memory, let's say. And then I have an implementation of the generic fraud-proof protocol, which is basically the idea of the bisection that allows to do the arbitrary computation. I will not present this today. But since it's popular to show the V-bytes these days, if you implement this with sMATT, the expectation is that for the most complex computations that will do like 4 billion steps, if you implement fraud proofs with sMATT, you will get, in the worst case, so in the non-cooperative case where the entire fraud proof bisection protocol needs to go on chain, the expectation is that the total cost will be less than 10,000 V-bytes. Which at today's fees is around $125. So not bad. I have a blog post in Delving Bitcoin that describes all these things. And yeah, demo time. So the last time I ran this demo, the very first command failed. So and I did at least one commit this morning. So wish me luck. So yeah, this is a CLI demo of Vault implementation. There is a nice autocomplete, so you can see what are the commands. And you have the Vault address. And so, well, let's go in the history because I have some commands. There is also a nice history which helps with this demo, so I don't have to remember the commands all the time. And so we found the Vault by sending a UTXO with that size. We found another one. We do another one. And these demos are all like, the transactions happen automatically, so whenever I want to send a transaction, since it's reg test, we can print money and transactions happen. So it's if you check the last block, you see that there is the last transaction was a 30,000 UTXO, which is the one sending money to the Vault. And now, if we list what the contract manager, which is this object that knows about all the UTXOs, knows, there are these UTXOs that it knows about. They are funded, so they're real UTXOs. And that's what these are. So there are Vault instances with some parameters, and there is no data inside because there is no data inside the Vault contract. And now what can we do to a Vault? Well, we want to start a withdrawal, and let's say we want to spend just the first two UTXOs. So the total amount of these UTXOs, you can see, is 10,000 plus 20,000. But we want to withdraw only 29,000. Right? So what happens if we do this? We wait for the transaction to be confirmed, and that should happen. OK, it's done. Again, we can go here. And this is the transaction that just happened. And you can see here that there are two outputs. One is 29,000 sats, and one is 1,000 sats. And that's because what the transaction that was done was trigger, the close that was executed was the one that I showed before, the trigger and recover, that also has the partial unvaulting. So the first two UTXOs are gone, they are spent, don't exist anymore. But now we have two new UTXOs. One is in the unvaulting stage, which is the next step of the state machine, and that's worth 29,000 UTXOs, 29,000 sats. And then we have another Vault instance, which is only 1,000 sats, which is basically your change that went back to the Vault. Now, what do we want to do with the Vault? Well, at some point, we want to withdraw, right? And so that's item 3. We want to spend this unvaulting UTXO, and we want to withdraw it. So we want that to finally go to the address we said before, and oops, that doesn't work. Why does that not work? Because, well, in our contract, we put a time lock, so we cannot yet spend it, right? And so BIP68 is the BAP that defines the time locks that we're using. And so what we can do is we can mine 10 blocks, and those are the blocks that we mined. And now we can try the withdrawal again. And this time the transaction seems to go well, and that's gone to the destination. And again, we can see that in the transaction that is in the last block, there is one output which is 29,000 sats, and is going to this address here that ends by 437, and that was the address. Hopefully, should be the address that we put in the trigger before. Yep. That's the address. And yeah, that's about it. And now let's start maybe. So now we still have 2 instances of the vault that are still funded. So now we can spend them as well. And here, of course, I'm playing from one command line, but you can imagine that there will be multiple parties involved here because the people withdrawing and the people trying to steal the money or people sending to recovery could be different entities. Could be you could have a watchtower, for example. And so now we have these 2 items, and we want to send the total amount, all of them, to another address. And that's confirmed. Now again, we have all the UTXOs are spent except the last one, which is the new withdrawal that you started. That's called unvaulting. And this time, someone was trying to steal our money, and we want to we want to recover. And we want to recover item number 5, which is the one we just created. And this doesn't need a time lock, so we can do it at any time. And this is done. And if we look at the transaction that just happened, this is sending to a fixed address, which is what we defined before as the recovery address. And now there is all the UTXOs are spent. So this is about it for the demo of the vault. And I think what's interesting is what does the code look like to implement something like this. And so in this file, there is the definition of the entire contracts. So we have 2 classes that implement these contracts. One is vault and one is unvaulting. And so the vault takes a bunch of parameters, which are these given here, and those are the parameters that go inside the script. And now in the definition of the clauses, well, first we create the next contract because we need that inside the code of the script, right? So we create the unvaulting script, the unvaulting contract. No, these are contracts, not contract instances. So those are just how the program works. And now we have 2 clauses here, which are the spending clauses. So I have 2, which is trigger and revolt. So trigger basically wants to spend the whole amount of this UTXO inside the unvaulting stage. And while trigger and revolt also has the partial unvault. So you want to send back some money back to the vault. And if you are spending many instances in the same transaction, as we did before, normally you will need to use trigger and revolt only once because you would probably need to just split one of the amounts. There is no need to split multiple UTXOs. So most of them it's cheaper to not split many of these UTXOs. You would use trigger for most of them. And so this is the entire script. Because all you're doing is that, well, you pass the index of the output, you pass what is the destination, and you pass the signature. And the signature is just to prove that you are allowed to do this operation. And so check, contra, verify checks that indeed you are going to the unvaulting contract. So this is the program. And well, if there is here, let's say we're using 0, which is there is no internal key. And the data and the index are the ones that are passed via the witness tag. So those are arguments that are passed to the close. And so this is all the script. So it's a very small script. And it does basically everything. And together with the script, we also define how the arguments that you need to pass via the witness are defined, including signatures. So this is not really an argument in the contract, it's just the signature. And this is the actual arguments that you are passing to the close. So this is, we are spending, we are triggering, and we are deciding destination, and we are deciding that's the output in the transaction. And we also define what are the expected outputs of the transaction, because the framework is not smart enough at this time to figure it out from the script. But we can just say, well, we know that if you do a transaction of this kind, we are going to have a close output that has index out e, which is we pass in the argument, and the contract of this index of this output is unvaulting, and then this defines what is the data contained inside the contract. And trigger and revolt is similar, it's just a bit longer because before doing the same script that we had before, so the second half is exactly the same, but it also allows to specify an additional output, which is where you're sending the money back, and that has to be a vault. So it's using the same program of the input, so this makes the contract kind of like recursive because you can go back to your own program. And again, there is no data there. And so this is the deduct logic that we saw before, and then the rest is the same. And then we also have another clause which is like, well, if we want to recover at any time, that we can do, and that's just sending the, this is using check contra verify to send the money to a predetermined public key, which is some taproot address, right? And so that's all the code for the vault contract. And then for the unvaulting contract, we have two clauses, which is withdrawal and recover. So withdrawal is just checking that indeed the money is going to the final destination. But first we have to read this destination. So this is some boilerplate that I simplified with some helper function, but this is basically doing check contra verify on the input to check that the data was indeed what we are passing. And then we check the time lock. And in this case, we don't need signatures because check template verify makes everything not malleable, so it should be safe to not have a signature, and so we're using check template verify. And the recovery script is exactly the same as we had before. And so that's all the definitions of the contract. And there is a test suite that actually I wanted to run before and I forgot, which hopefully it works. You can run tests. And I think if you want to implement these kind of things, working with tests rather than with interactive CLIs, it's a bit easier. And the suite also generates a nice report that shows some of the transactions that were produced by the tests. So this is for other things, but the vault transactions are here, and there are some estimates on the size of those transactions, so that's good for comparing. And so if you're implementing these things, how does it look like? So this is examples of tests in the vault. So we have this manager, which is the biggest class in this framework that is able to track all these UTXOs and work with them. And so we define the contracts here at the top of the test. So those are different variants of vaults, basically. And this is just creating the contracts. And if you are looking at this, so this is creating a contract instance. So this is a class that is defined in the framework, which creates a contract instance which is funded with some amount, and this is the contract which is the one that we defined before. And so we create whatever arguments that we want to pass. So this is to create the destinations of this transaction. Here we are sending to 3 different addresses. And so this is a contract instance, and we can basically call it a bit like a function. So we pass a signer, so this gives enough knowledge to know how to send this transaction. This passes the arguments, and when you execute this line, this is actually using the manager to send the transaction and track what is produced by this transaction using all the framework we defined. And we know that we expect we will get some instances back because this produces some new contract instances, which is the second contract. And that's a contract instance of a different type, which is the unvaulting stage. And so, this is using trigger and recover. If you do a full flow, which is trigger and withdraw, like it will look like this. You have, again, you do the trigger transactions, and then you produce a spending transaction. Well, those are some of the examples that are a bit more complex. And here is an example where you have to mine some blocks before you can do it. But again, you can ask the manager to wait for the transaction to be spent, and then that will produce the final results. And so that's the thing I wanted to show in terms of code, that like defining the framework, there is really not much more to do other than defining the script. So you do have to understand scripts to start implementing these things, but actually the framework is already smart enough to be able to abstract all the common boilerplate of like encoding, decoding the witnesses, and figuring out these things. That actually the tooling for these things tends to be quite a lot of the work to produce these demos the first time that you do them, and yeah. So yeah, the contracts. Don't know if it makes sense to go look too much in the contract, but yeah, basically there is a bunch of classes that are the ones that we are extending earlier that have all these functionalities that are already implemented to get the taproot addresses, to generate the taproot trees and all these things based on the clauses. So that simplifies a lot all the logic of all these contracts. And the manager is the bigger objects in this, which knows how to do all these things. It's connected to the RPC, so it can send transactions, it can receive new block, and make sure it's not production ready. This is good for demos, good for reg tests, but of course you need something more complex for real world implementations. And maybe I'll stop for a moment if there is any question on this so far. No? Yeah.
Scripts again for the unbolting?
Yes. So yeah, this is the unbolting class, and so those are two clauses. So this is withdrawal.
The on-chain, so we looked at last block, like the actual script that the chain.
Oh, was that the last that we saw? Because maybe we did other. Which screen was it here? Was it here? Yes. Because this one was. Oh, this was a withdrawal. So this is the spend from the unbolting state. Which one do you want to see? Which spend do you want to see? Because
I just want to see the script. So where's the check contract verifier?
so, well, you can decode this transaction, I guess.
Yeah. So this looks a lot more efficient than like when I was looking at the outfall.
It's not more efficient, but it's so when I did some comparison, so Upvolt, it's optimized for this use case, so of course it's not going to be worse, right? For the exact same features as Upvolt wins by a little. Like I didn't find any example where this was more than like 10% heavier, right? But the advantage is that this one is more flexible because you are building the features yourself. So if you want a vault with different features, you can even build the vault with less features because maybe you don't want to have a recovery on the vault phase, or maybe you don't want to have the trigger and revolt, and so you have only one spending condition. So you can find probably some situations where this could even be cheaper than vault because you don't need all the features, for example. Or if you want more complicated constructions, you can do that as well. Or if you want to have multiple, so one thing that is tricky with Upvolt is if you want to have multiple spending conditions, both using Upvolt, that doesn't work very well because Upvolt only removes one of them when you call it. So you would have still a leaf with Upvolt, while here, because you are explicitly saying what is the next contract, you can have both leaves still sending to the same contract, so you don't have this problem. So it's more general than Upvolt and slightly less inefficient in some cases. It could be more efficient in some other cases. And yeah, that's why I had this example of I made a report at some point so that you can see the transactions. If you go to the vault, there was a gist somewhere where I had the comparison, but I don't remember where it is. Like this is a transaction that has 3 vault inputs, and it's so this is a trigger transaction, and it's like 400 bytes, which is probably very similar to what you will get with Upvolt. And okay, so the next demo may be. So how much time do we have? It's 10 minutes. So maybe we don't do a lot of other demos. Well, there is. Let's play a quick game of rock, paper, scissors then. Unless if there are questions and people want to ask something, maybe it's interesting to give, Okay, let's play rock, paper, scissors. So yeah, we have 2 terminals here because we have 2 players, and so we want, like, it is implemented in a way where you can play on both sides. And so, well, we are playing with Alice on the left, and we are playing rock, and we are playing with Bob on the right, and Bob is playing paper. So we expect Bob to win. And so I'll show you execution, then if you have some time, I can show a little bit how the smart contracts work. And so, well, Bob is playing the move. So the first to decide the move is Alice. I'll explain before why this happens even before the smart contract is created. Then Bob plays the move, broadcasts. Bob still doesn't know Alice's move. And, well, Alice knows that Bob wins. Bob is waiting for the adjudication because Alice didn't broadcast the transaction. So now we let Alice broadcast, and now Bob saw the transaction on chain, and this happened. So, well, it works. And for me, the interesting thing is how much code you need to do these kind of things. And if you look at the contract, well, let's not see the contract because we don't have time, but we have two players. So here, it's an example of code where each player only has its own code. So there are two parties. And so they establish a socket because there is some communication here that happens off-chain, where they exchange keys, for example, and stuff like that. And then once the instance is funded, Alice already committed to the move inside the contract. And so the contract on chain starts here. So here we're on Rectest, so we fund the instance with money directly. And so Alice is just waiting for Bob to play the move. And so Alice has the instance of the contract because she saw it on chain. And just to wait for this to be spent, there is a method in the manager that you can say, okay, I'm waiting for this to be spent. Let me know when that happens. And when it happens, you already get another contract instance, which is the next state of the contract. And on this contract instance, now it's Alice's turn to make the move. Well, Alice will figure out, well, who won. And then the outcome will be exactly the name of the clause. And so you actually spend this again by, you call it a bit like a function, you pass all the arguments, and this actually makes a transaction on chain. And so the Bob's code looks very similar. And yeah, but it plays the other transaction that we didn't see there. And so that's the main thing that I want to convey, that like once this framework starts to have all the pieces, like if you have an idea for a smart contract that you can represent as a state machine, which is mostly any protocol that you can do with smart contracts, going from the state machine to the implementation is pretty straightforward, generally speaking. And so I hope that inspires people to play with these ideas. There are so many things that can be done with smart contracts, and yeah, if anybody wants to play with these things during the hackathon, I have a slide with a bunch of other ideas that are not yet implemented. Some of these might be probably too complex for a hackathon. Some are easier. And yeah, let me know if anybody is interested. I'll be available.